This is a pleasure for me to introduce the first speaker of the day. Although he hardly needs any introduction, I will say a few words about Paul. So, as you saw from talks yesterday, Paul has contributed substantially to the understanding of rare event simulation algorithms, and not only that, in general in the area of stochastic networks, which is the theme of this whole activity at the Newton Institute, and also to large deviations theory. It will be very difficult to actually say all the contributions of Paul. He's the chair of the applied math departments at Brown, and so he's going to talk about interacting particle schemes for rare event estimation today.
Thank you, Jose, and I'd like to thank Peter for the invitation to speak today. I had the pleasure of being at the last two RESIM conferences, the one in Bamberg in 2006, and then the one in Rennes in 2008. And I learned about the interacting particle approach to rare event estimation there. And it's a different scheme. I was familiar with the standard splitting, but this interacting particle scheme had certain properties that were identified as being very nice. For example, they have the property that you can control the computational effort with each simulation, which is a different sort of feature. And so I was curious, how did these schemes perform relative to the existing schemes? In particular, how did they perform relative to other splitting type schemes? And I spent a long time thinking about that, more than a year, maybe close to 2 years. And so what you'll see is what I've learned about that in the time. It's not quite complete, but it's pretty far along. I should mention that let me use this. Is this plugged in?
Maybe you have the microphone on?
No.
Related to as Peter was saying, that they don't. This probably is disabled if you don't have.
No, I have it on. That's on. I could have brought my own. Have you used this? Yeah?
Oh, it's not even working. Oh, yeah.
You're working now? Okay, thank you, Sean. Peter, do you know about this? Do you have to do anything to turn it on?
Oh, there you go.
Okay. So let me get back to the talk. So I should mention this is joint work with Yi Kai, who's currently a graduate student at Brown. Let me start by just giving an outline of what I'd like to say. Start with the problem formulation. It's the standard problem that we use to analyze these types of algorithms, hitting probability, hitting a rare event before hitting a typical set. Talk about construction of the IPS estimator. I'll assume that most people are not familiar with it. I'm going to work in the setting of the light-tailed random variables, so we'll look at asymptotic optimality. In particular, the performance measure will be described by the large deviation asymptotics of the second moment of the estimator. I want to talk for a while about how this problem is difficult, how it differs from ordinary splitting. There are a lot of non-standard features. And then it's interesting that even though basically the rare event problem that I'm looking at is a small noise large deviation type problem, the right way to think about this, if you want to do the analysis, is actually in terms of something called the large deviation for occupation measure, which is That's probably the thing that took me the longest to figure out in this context. I'll then, to simplify the exposition, stick to a one-dimensional problem just to make everything as straightforward as possible. Because the analysis is based on occupation measures, it's relevant and useful to introduce what's called the relative entropy representation for the second moment. That's the key to the analysis. And then I'll just state two main results. One's the large deviation limit for the second moment as the large deviation parameter goes to its limit, but with the number of particles fixed. And then that gives us a certain rate of decay of the second moment, which need not be the optimal one from the point of view of rare event simulation, and then talk about asymptotics as the number of particles grows. And then some remarks on what happens dimension greater than 1. All right, so the setup is the following. I have a sequence of Markov processes. I deviate from any tradition I've ever seen in large deviation. I'm using m for the large deviation parameter rather than n, which I'm going to keep for the number of particles. I'm still getting used to this. So what does that mean to say that that sequence satisfies the large deviation principle? Loosely speaking, if you give me a trajectory phi, and I look at a suitably interpolated version of the process, then the probability that it stays in a small neighborhood of phi decays exponentially with exponential rate of decay given by the rate function, and m is the large deviation parameter, and the rate function takes some standard form in terms of an integral along the path. And just often m is representative of some physical parameter in the system, such as buffer size. So the problem that we're going to use to study the interacting particle system is this standard one in the rare event simulation community. Start at some point x and look at the probability that we hit a rare set before hitting a typical set. These flow lines indicate the paths where the rate function is 0. These are the law of large number limits. So this picture is supposed to suggest the mass being swept into A, and therefore hitting B is difficult. So the event of interest I can write out in the following way. I let C be the trajectories that hit B before hitting A. So conditioned on starting at this point x, I want to look at the probability that I land in the set of trajectories C. I'll call that Pm of x. And under some mild conditions, on the boundary of G and properties of the rate function, we know what the rate of decay of this probability is. It's simply the solution to this variational problem involving the rate function. And I'll call that thing gamma of x. So that'll be the rate of decay of the event of interest. Okay, so the construction of the estimator that I want to talk about today. I'll show the literature in a few minutes, at least the literature that I know that describes the beginnings of this algorithm. I'm not sure. People will tell me today what really is the beginning. Maybe Francois can tell me. But it's several papers involving Pierre Del Moral and some co-authors. I'm not sure I've tracked down its exact origins, though. But here's one version of the algorithm as I understand it. We insert a number of thresholds between the starting point and the target set, the rare event that I'm trying to hit. Jose called them milestones. I'll call them splitting thresholds. I've ordered them so that I've put a large deviation parameter on them because the thickness, the spacing between them will scale with that. And I've ordered them in a decreasing fashion, an increasing fashion so that you hit the target set when you've hit the highest threshold. And the algorithm starts with cap n particles located on the initial point x. And then it's a recursive procedure. I have to tell you how you're going to simulate particles up to the next threshold, and then not all of them will make it to the next threshold. Some of them will be swept back into the typical set, and so you have to reconstruct based on that. So here's the first step in this sort of recursive procedure. I want to think of it as being divided into what I'll call the transportation step. That's the step of bringing them up to the next threshold, and then the resampling step. So the first step, this transportation step, I'm looking at the case here of 6 particles. Not all of the particles will need to be simulated up to the next threshold if they're there already. So in this figure, I have 4 particles sitting here in threshold with index k minus 1, but not yet in threshold with index k. I have 2 sitting that on previous simulations overshot and jumped into the next threshold. So I don't need to transport these. They're already there. These I need to transport. This is supposed to show some trajectories of the random walk. These 2 got swept back to the typical set, and these 2 made it up. This one made it up just to the next threshold. This one actually went into 2 thresholds up. So after the simulation step, the transportation step, I now have 4 particles sitting in the kth threshold. And I want to reconstruct to get the original 6 back, and that's done according to just sampling according to uniform distribution on these 4 locations. So in this scenario, we ended up with 2 particles here, 2 particles there.
They are in different thresholds.
They are in different thresholds because you're not limited to jumping into the next threshold. The simulation could take me over, right? This is a discrete time random walk. There's nothing that, especially when the spacing between these is scaling with m, there's nothing to stop me, there's nothing to stop a particle from jumping over all the way to the next threshold or many thresholds.
So but when do you stop the transportation step?
When do I stop it? I stop it as soon as the trajectory ended. So these piecewise affine, this is supposed to be time. So this would be a discrete time step of the underlying chain and then a next time step. So it made it into the next threshold here. Two discrete time steps of the true clock for the process. Step 1, step 2, it's now there. There may be many steps involved in going to the absorbing set. In this one, there were 2 steps of the underlying time index for the Markov chain. It didn't make it to the next threshold here. It did make it here, but it jumped all the way past this threshold into the next one. In continuous time, this wouldn't happen, but when you implement these things, they're in discrete time. So that's one of the things that makes the analysis sort of nasty, is there's all these different possibilities. Are you making it to the next threshold? Are you going past? And so on. So anyway, let's say that 4 did make it. Then I have to resample. We use the uniform distribution, get back the 6 particles. So how do you form an estimator from this? Each particle, because of we're always using the underlying dynamics of the random walk model, each particle is distributed according to the first entrance into the threshold k. So you get a nice estimate for this conditional probability just from the fraction that make it. Right, nk divided by k. And so the product of these gives a nice unbiased estimate of the probability you're interested in. That you make it all the way from the starting point to the last threshold. Okay. So this is the estimator, the product of the ratio, the fraction that made it up to each successive threshold. And in the usual fashion, this gives me one sample, one estimate, and we'll average some independent copies of this to get an overall estimator. So again, this is some of the literature that introduces this. There are variations that I know of, but I wanted to stick with what seems to be the simplest model. And I'd be interested in updating my knowledge on the bibliography. All right, so let me talk about a performance analysis for this type of scheme. So I should mention, previous performance analysis tended to focus on letting the number of particles go to infinity first and then letting the probability of interest get small. And the problem with that, at least from my perspective, is that for an algorithm that's advertised as being good for controlling work, that's the wrong limit. I really want to fix the number of particles, look at the performance with the number of particles fixed and the computational effort, predictable. And then, after we've sent the large deviation parameter to its limit, maybe consider what happens as you vary the number of particles. All right, so the performance analysis, this is standard. It's an unbiased estimator, so bounds on variance follow from bounds on second moment. Again, this is sort of standard in the rare event business, rare event simulation business. Jensen's inequality tells me an upper bound on the rate of decay of the second moment, which says that basically the best you can possibly do for the second moment is the square of the decay rate of the original probability. And the goal of design is to try to get close to that decay rate. So, what are some of the difficulties in the analysis of this, particularly with regard to ordinary splitting? The first thing is, and this was sort of alluded to in Jose's question, the natural timescale for the process, the count of the clock for the process, is not the natural timescale for the algorithm or for the analysis. The hitting time to the thresholds, that's where everything that's interesting happens. The underlying clock that goes with the process really is not so meaningful. Unfortunately, the large deviation properties of the original process are on that clock. The standard splitting, the way that we can analyze second moments there heavily uses the fact that after we split, the particles are independent from that point on. So I can really just, the only thing I need to know is sort of the history. When did they split? After that, they're conditionally independent, and I can exploit that independence plus sample path large deviation properties to do the analysis. In contrast, here you have this resampling that recouples the entire collection of particles at every threshold. And these thresholds are dense. The gap between them is order 1. So they're constantly getting recoupled. This follows up on something I said previously. The recoupling is what stops us from using, in any sort of straightforward way, ordinary large deviation analysis, ordinary large deviation properties of the underlying process with the small noise scaling. And then the last problem that makes it somewhat difficult to analyze, if you wanted to just consider, say, the many particle limit, which again is what people have done before, then sort of law of large number effects dominate there, and it's somewhat easier. But here we really want to get estimates that go all the way from, say, 5 particles to large number of particles. You need some technique that handles all of those seamlessly. So I guess this is probably the most useful comment that I'll make in the talk, is that the good way to think of this is not in terms of small noise large deviation, but in something that Dan Scavara would call occupation measure or empirical measure large deviation. The quantity that I'm interested in, here's the estimator theta m. The quantity of interest is the second moment, which I write out in terms of the fraction that made it up to the next threshold. It's this quantity squared, and I'm taking the product over all of the thresholds. Now, the number of thresholds is going to scale proportionate to m. And so if I just rewrite this in an exponential form, it starts to look like something that looks like some kind of a quantity that you could apply some large deviation analysis to. Namely, it's a sum. So let me normalize by dividing by k on it, k to the m. I get this factor out in front. It's 1 on k to the m times the sum of these logarithm of fraction that make it up. So if I rewrite this, I can rewrite this in a standard way using the empirical measure. I count the relative frequency of the numbers of times that I had a given number of successes making it up to the next threshold. I record them in this empirical measure, and I can rewrite the performance measure. I can rewrite it in terms of an exponential against the empirical measure. So that's a very different perspective. I'm going to need to work with somehow the ergodic properties. Think of this as a random process, the fraction, the number that make it up to the next level. Think of that as a random process. It's really somehow large deviation ergodic type properties of that process that are relevant to the asymptotics. Okay, so I want to say what we can say about the analysis of that problem. To simplify, I'm going to switch to a simpler model, namely just the one-dimensional model, no state dependence, just a random walk model. So my model now becomes a random walk with IID sum ends. I assume the theta I have a mean that points to the left, so I imagine 0 is going to be the absorbing point, or negative infinity to 0 is the absorbing set. The random walk is unlikely to hit this set, unlikely to hit 1 before hitting 0. And I'll start it off just a little bit to the right of 0. I we'll make the following assumptions. I only need moment assumptions on mu, but to simplify, I'll just say that it's bounded here. I'll assume that it has some probability of allowing the particle to move to the right so that it's a non-trivial problem. And the spacing that I'm going to use for the thresholds, I'm simply going to take it 1 on m spacing. So this is one of the features that I want to emphasize that's going to be interesting for the interacting particle system. I'm not going to make any a priori connection between the spacing of the thresholds and the underlying distribution. I'm not going to look for any subsolution property, supersolution property, no Lyapunov. There's no connection at all. I'm just using a regular spacing. So I'll need some notation in order to set up the results and tell you what happens in that setting. Let me let K be the generic index for the thresholds. Let me let S be the index for the particles. And I'm going to use the following notation. Z will be a collection of particles. This is the kth threshold. The dot indicates that's the index for the particles. These are the particles prior to transportation, so they're sitting in the k minus the kth threshold. I transport them. I call the outcome y. Some of these may not need transportation at all, and they'll just be left alone. Some of them will be transported and they'll hit the absorbing set. And some of them will be transported and they'll make it up to the next threshold. That collection I'll call y. And then resampling only among those that made it to the next threshold, I'll call that z. And it's like Henrik yesterday. I'm just saying what I already said. Z are the ones that are located and need transportation. These are the ones prior to transportation. This is the location after transportation. And let me just let delta be the absorbing set. Okay. Then the key quantities to construct the estimator are the following. I will be the number of particles that need transportation. I'm going to have to distinguish those that need to be simulated from those that are left alone, and in particular, the number of them. And then n, this is the crucial number at each threshold. That'll be the number that make it up, so that I've defined before. And just a reminder, so this is the quantity that I'm interested in, the empirical measure for the number that made it up. Okay. So I'm going to put that on hold for a second, and I'm going to switch to something a little bit different because I have to come back. In order to understand the limits of this is an exponential integral. In order to understand what this does when m goes to infinity, I'm going to use something that I've grown very fond of. It's the connection between relative entropy and exponential integrals. So I'm going to take a few minutes to talk about what that is for those who have not seen it before, and then tie it back to the problem at hand. So there's this very nice connection between exponential integrals and relative entropy, which underlies virtually anything in large deviation, whether you've seen it there or not. It's there lurking in the background. So let me let S be a random variable with some given distribution gamma, and let F be any bounded and continuous, bounded and measurable function. Then there's this very nice formula that gives a variational representation for exponential integrals. Namely, if I'm interested in this exponential integral, I have to take the logarithm and put the minus sign in just to get the signs to work out right. But this quantity has this nice variational representation. This will turn out to be relative entropy. This is the underlying distribution of the random variable S. I'm going to perturb it. I'm going to switch from gamma to some other distribution eta, and then this will have the distribution eta. And I pay a relative entropy cost, and then I take expectation under the new distribution. And that gives you a variational representation for that exponential integral. This is super general. The S can take values in all sorts of general spaces. And the cost that I pay to perturb the distribution is relative entropy cost. And relative entropy turns out to have many, many nice properties that are exploited over and over again in large deviation theory. So that gives me a representation for one random variable. What's very nice about this representation, though, and very, very handy in large deviation type theory, is that you can decompose the relative entropy into the contributions from different noises that enter the system. So I'm going to just write it out for the case of a two-step Markov chain, but you can imagine the generalization, and this thing is called the chain rule. Well, the thing I'm going to use is called the chain rule for relative entropy. So instead of one random variable, suppose I take two steps from a Markov process, S0, S1. I start off with an initial distribution gamma 0 in a transition kernel gamma 1. The chain rule tells me how to decompose relative entropy for measures on product measure, measures on product space. So here's my underlying two-step measure for that Markov chain, initial distribution in transition kernel. Let me consider the two-step measure for any alternative Markov chain, call that eta. Then the relative entropy for the two-step process, for the measures for two steps, can be decomposed into a contribution for the first step, and then you get a sort of a relative entropy for the perturbing the conditional distribution of the second step relative to the original distribution of the second step, conditional distribution. And then you integrate that against the new distribution for the first step. The point is that relative entropy decomposes in a very nice additive way with a new relative entropy course brought in for every new noise that enters the system. And what that allows me to do is to write this exponential integral in a convenient way. For example, in the setting of a two-state Markov chain, I get a variational problem where I can separate out the course in this additive fashion. I write it as an infimum over some relative entropy course for perturbing the distribution, and then expectation of the functional of interest against the perturbed distribution. All right. I'm going to use this with waving of the hand in a second, and just give at least a little bit of background on where it comes from. All right, so this chain rule for relative entropy, I claim, will give me a very nice representation for the second moment in the interacting particle model. I mentioned that one of the difficulties of the interacting particle model is that it really emphasizes the times when I hit the thresholds rather than the underlying clock of the original process. So in view of that, let me define the transition kernel that's associated with the process. In other words, alpha of x dy, that's going to be the measure on where I land after I reach the next threshold, conditioned on where I start. But I'm shifting everything relative to the left edge of the threshold. So let me show you the figure. Here's the k threshold. I'm not in the k threshold yet. I'm sitting somewhere between the two. Let's say I'm sitting at this point. I'll measure that point x by the distance from the past threshold, the most recent threshold. And then let's say I simulate, I land at this point over here. What do I want to call that point in terms of this transition kernel? I'll call that point y. It's just the distance that I've made it past the next threshold. So if you can absorb, instead of trying to absorb this, you just look at this picture. I'm looking at the probability of going from x to dy under the original dynamics of the process. And I call that alpha. And as k gets large and as m gets large, because 0 sort of recedes to infinity, this thing approaches some stationary transition kernel. So in this one-dimensional problem, if I don't want to look at the underlying clock of the process, I can look at this transition kernel instead, and that tells me what happens at the times of interest when I make it to the next threshold. Okay, so I'm going to write down a representation for the second moment of the original interacting particle system. It's going to be in terms of relative entropy. That means I'm going to consider some perturbed or controlled dynamics and pay a relative entropy cost to perturb them. So I'll use bars to indicate the controlled interacting particle system rather than the original one. Otherwise, it's all constructed in exactly the same way, except I'm going to be using controlled distributions rather than the original distributions. So I'm going to be perturbing the transition kernel, the true transition kernel of the dynamics, and I'm going to be also perturbing the resampling measure. I won't be using necessarily uniform, and I need that in order to have the representation hold exactly. So I'll try to go through this a bit at a time. This is the quantity that I want to analyze. This is the thing that measures the performance of this scheme. It has a very nice representation in terms of sort of a stochastic control problem. It's going to turn out to be an average cost per unit time type problem. So let me just go through it slowly. The controls are the perturbations from the original distributions to the new distributions. I'm not going to use alpha to simulate up to the next threshold. I'm going to use some new transition kernel. And I'm only going to use that for the particles that actually need transportation. And I'm not going to use the uniform distribution once I look at the particles that have made it up there. I'm going to consider any distribution that I want to, perhaps some biased resampling distribution. And then, and then this is the original functional of interest, but inserted there is not the original number of particles that make it up. Rather, it's the controlled number of particles that make it up. And then this sum indicates that decomposition of relative entropy according to the chain rule, and the normalization 1 on m is due to the 1 on m sitting out there. So this gives an exact stochastic control representation for the second moment of the interacting particle system. Again, this is why the perspective of looking at it as an occupation measure problem instead of a small noise problem was sort of important to make progress. This it's a little bit unusual looking stochastic control problem, average cost per unit time, but it's actually not so different. Once you get used to the notation and whatnot, it's one that you can handle using standard methods with a little adaptation. So specifically using that representation, I can evaluate the limit of this quantity using that stochastic control representation. V star is going to be some sort of nonlinear eigenvalue solution of average cost per unit time problem. Let me just say a few words about what I need in order to prove this limit. I don't need any additional assumptions for the lower bound, and that's important because the lower bound, that is the lim inf of this stuff, is bigger than this. The lower bound is the one that's interesting from the point of view of performance of rare event estimation. That requires no additional assumptions. The upper bound, anybody who's done average cost per unit time or ergodic control knows that you need some kind of ergodicity conditions in order to get the two bounds to coincide. Not surprising here, I have to impose some additional conditions. So this is not a defect of the mathematics. This is a true statement that you're going to need some additional conditions to get the reverse inequality of the second moment. So, in that context, though, I would note that we already know an a priori upper bound, namely 2 gamma, just out of the Jensen's inequality. We already have separate from this bound, we already have an upper bound of this form. That's just out of the Jensen's inequality. So, I'm going to write down an expression, an exact expression for V star. I don't expect you to absorb all of this notation. It's a bit of a burden. I wanted to write it down just so you could see the form that it took, so that when I let the number of particles get large, you could imagine what's happening. But basically, the expression is going to involve a stationary distribution for the n particles. I've turned this into some kind of stationary ergodic control problem. And m is going to be a measure that's supposed to be a stationary measure on the joint distribution of all n particles. In order to evaluate the asymptotics of so this quantity is somewhat complicated. There's a lot of terms that I need to evaluate the asymptotics of. It depends on the number of particles that need to be transported. It depends on the number of particles that I have before I do the resampling. There are a whole bunch of details that need to be addressed in the limit. It's all built on top of basically a stationary distribution on the n particles prior to the transportation. I need to look at the marginal of that distribution, the number that need transportation. I need to look at the conditional distribution of the particles given the number that need transportation. I need to state a transportation control. I need to identify from this measure in the transportation control the number that I'll have available for resampling, and I'll need to talk about some stationary resampling measure. There's a lot of notation, but in terms of these quantities, they're supposed to represent some kind of stationary system. You give me this joint distribution on the n particles, you apply the transportation control to simulate up to the next level, you apply the resampling control to add up to get the full number of particles, you should return to this measure. It's a consistency condition between all of these quantities, and indeed this is the formula for the cost under all of those controls, and the V star, the limit, is the solution to this problem. So again, if you're familiar with average cost per unit time ergodic control, this might not look so shocking. If you're not, it's what you have to deal with. There's no way around it. So in any case, I look at the cost for all of these stationary systems under these distributions and various controls, infimize over all consistent systems. That's V star. So to summarize, what we've ended up with at this point for the second moment of the interacting particle system is a lower bound in terms of that control. I'm sorry, I put back in because I want to send n to infinity now, but now we've passed to the limit on the large deviation parameter. We've ended up with a lower bound in terms of the solution of that average cost per unit time problem on the performance. Typically, this is actually going to be an equality. If the ergodicity conditions hold, which I'm not assuming, but if I do put those in addition to the moment conditions, then I'll have this equality. But in general, I'll at least always have this. So imagine, just for the sake of argument, that this is just an equality at this point. So what we get is the performance is measured in terms of the solution of this average cost per unit time problem. And then the next question is, well, how did that really depend on the number of particles? Is it equal to 2 gamma? Is it smaller? What's the difference? Because this is measuring the performance. This is measuring if there's a big gap between this and this, then you could argue that maybe some other schemes that come much closer to this exponential rate of decay are going to perform much better. So I really want to know something about what is the gap here. Well, that means you have to look at that formula, that representation that I gave for Bn star, and consider the limit as n goes to infinity. You can analyze that using properties of relative entropy. And it's interesting, it turns out there's no large deviation involved anymore, but just using lower large numbers and central limit properties of the underlying transition kernel, I can evaluate the asymptotics of this as n goes to infinity. This bound holds for, I can get a bound of this form for all cap n, and actually there's an equality, an asymptotic equality that I can obtain. So in other words, you lose something proportional to 1 on n.
Gamma star equal to gamma?
Ah, gamma star, sorry. I guess I got excited with the stars there. That's just gamma.
Gamma star is the gamma.
Yeah, it's just the gamma. I guess.
Negative sign in the lim sup probably shouldn't. Oh yeah, sorry, it's a trivial inequality.
Yeah, that's the standard
Yes.
inequality. Right. So as far as the specific value that this takes, this is the asymptotic rate of decay of the second moment for a fixed number of particles n, and we lose roughly some constant over n in performance as compared with the best we could possibly do. All right. So this expression was the exact asymptotics for the second moment for fixed n. And then the question is, how does that compare with the best you could possibly do? And what we get is that there's a loss.
But this is regardless of the, how do you put the...
It's independent of the thresholds. I mean, the constant will depend on the specific spacing between the thresholds. And I've written it as inequality, but this is for all n. If I want an asymptotic result as n gets large, then there's inequality here.
Is it tight?
Yes.
It's tight.
Yes. So this is interesting because it indicates two properties of the interacting particle system that are different from ordinary splitting. The first is that I needed no relationship between the threshold spacing and the underlying dynamics to get something that's reasonably good, namely this rate of decay. I mean, that's not too, it's 1 on n, it's proportional to 1 on n or. So I don't need, even with ordinary splitting, you'd have to be pretty careful on the splitting thresholds to get them to match up very, very nicely with the likelihood of making it to the next threshold. There's a robustness in the interacting particle scheme that says you don't have to be so careful. You don't need to do that. But what you do lose is you lose this factor on the decay rate. So it's made pretty precise exactly how much you lose.
So the constant is probably very, very hard to compute.
You can bound it, though, without too much difficulty. Yeah. It has some crazy formula, but you can get some useful bounds out of it.
But that one depends on the distribution, of course.
That one depends on the distribution and the specifics of the spacing.
So the number of particles at the end will have to depend on properties of the distribution. Just have to, if you want to get like the epsilon close to the optimal decay rate, you need a number of particles that you actually get.
Yep. Okay, so now I have a few minutes left. I wanted to at least say a few words about higher dimensions and try to make it a little bit more tight, the comparison with the ordinary splitting. So in some prior work with Tom Dean, who's here at Cambridge now, and this is following some work with Hui Wang on importance sampling, we established a connection between the performance. Yeah, Jose.
Is this result like, if you have like 2 dimensions, maybe you're going to say exactly this right now. If you have 2 dimensions, then there is no such a thing as just place the threshold, whatever, because you can place.
So this robustness is a one-dimensional property, and the point of what I want to say in a minute is that it does not extend to multi-dimensions. It extends in sort of a one-dimensional way to multi-dimensions. So in some previous work, we've shown that necessary and sufficient conditions for good performance of ordinary splitting is tied to a specific design criteria, namely the thresholds have to be level curves of a sub-solution for a certain related PDE. So I want to go back to this, the multi-dimensional framework with X, B, and A as illustrated. This is unfortunately going to come across as maybe just notation for a bit, but again, if I have a rate function that takes this form, let me define a Hamiltonian in terms of a Legendre transform. This is the local rate function, so this tells me something about the probabilities of locally making it up to the next threshold. To see that there should be some connection between solutions of a PDE involving this and the splitting scheme, let me just make the observation that using the large deviation properties and the specific of the spacing, if I have a mean number of particles m that I generate in the ordinary splitting each time I reach a new threshold, and I use this spacing, log of m on little m, then it turns out that this is the expected number of particles that will make it to the next threshold, given that I have one now. So if I want supercritical branching or supercritical branching would occur if this is bigger than 1. That's something I don't want. I want subcritical branching, which means that this, the h, should be greater than or equal to 0. So if you just look at it from the point of view of trying to bound the number of particles, keeping them from growing exponentially, it's very natural. So this is the gradient of the function I'm using to establish the thresholds. it's very natural that this function should be greater than or equal to 0 as a means of controlling the number of particles. And indeed, that suggests a sub-solution property that you should insist that hold for the function w that you're using to construct the thresholds. Just a reminder of the notion of asymptotic efficiency. We'd like to have a bound like this. So let me just summarize the ordinary splitting and then the interactive particle analog. Consider a continuous function w. Suppose that the splitting thresholds are exactly of this form. So in other words, the spacing is log m. M is the mean number of particles per split. And then I divide that by the log deviation parameter. Then the conclusions are that the number of particles will grow sub-exponentially if and only if this function is a sub-solution for that related PDE. And if it's a sub-solution, then I actually have this limit for the second moment. The best we could do is 2 gamma. A sub-solution of the PDE will always be less than or equal to gamma. And so you end up with this sort of natural design problem. Your thresholds, you want to design them on the basis of a function w, a sub-solution with as big a value at x as possible. And this leads to the various schemes that we talked about in the past. So the bottom line is that this is the rate you can obtain in w. You need it to be a sub-solution for this to happen. So there's this 1 degree of freedom in splitting that you get for free. So here's a way of formulating that shows how it enters a statement. Yeah, I should mention, so at this point in conjecture, the tightness proof is not complete in the multidimensional case. Granted the tightness, the following holds. Consider any monotone non-decreasing function g. So I'm going to use w to select the thresholds, but I'm not going to be very precise. I'm not going to, in particular, I'm not going to pay attention in the sense that I'm going to allow some function g when I compose it to w to maybe patch up for some mistakes that I've made. So consider, let's let w select the thresholds as level sets, and then compose w with some function g. As long as the composed function is a sub-solution, then this lower bound holds. And then the natural thing to do is, of course, to then just soup on g for the best possible bound. So that's a sort of mathematical way of saying we've got some extra robustness in one direction, the freedom to choose this function g. A few remarks, and then I will be done. So this repeats somewhat some of the things I said previously in comparison to ordinary splitting, which requires that w be a subsolution. Here I have this extra degree of freedom. I get to compose w with some scalar function. If you was lucky and somebody handed you a function w that, say, was a subsolution or even better still a solution, if I use that for ordinary splitting, then I'm going to get best rate of decay. If I use that for IPS, I'm always going to lose something. So IPS has some extra robustness, and it has some built-in loss that's automatic. So it's a trade-off. 2 final remarks. This was all under the asymptotics. The statement was all under the assumption that this is a subsolution. If there is no function g that turns w into a subsolution, and you use w to design the thresholds, easy to construct examples where the scheme behaves very poorly. So the subsolution property, modulo this strange transformation, is still a necessary condition for good performance. And one last remark. All of this is under essentially what's called the continuous statistics setup. It does not cover queuing systems. It's just smooth, spatially varying statistics. It's enough of a mess. There's enough difficulty with the smooth case. So, okay, I'll stop there.
So, I mean, I was wondering how much, like if, first of all, couple questions. First of all, how many subsolutions do you anticipate there can be? I mean, are the level sets really fixed, or could it be different level sets They're function different, very different level sets, but both sub-solutions. Is that possible?
So you mean using the function g to compose?
Not G, just the W itself. Because once you, G is G is not going to change the level sets. G
That's
is
right.
So could you have a function with very different level sets that both sub-solutions?
Oh yeah. I mean, this is one of the mysteries of using the sub-solutions in the rare event analysis, is that there are many sub-solutions. So you can get lots of different looking asymptotically optimal schemes.
And then if you got unlucky and you just couldn't find the right a function that's a sub-solution, could you get away with taking log m squared particles or something? Just
No.
yeah, but there's no fixed.
I didn't say it, but the first thing we did was we very slowly increased the number of particles with the large deviation parameter. That's a much easier problem to analyze, but it's sort of cheating because the whole point of the algorithms is that you control the total work. But if you slowly increase the number of particles, you get this, it's easier and you get the same result.
One of the reasons I was asking about, the C's, what your limit shows is that you need to send n to infinity, right?
If you want,
Because
if you want to get rid of that loss, if you want to get rid of that C on n term,
but you have to, because you are going to replicate this thing to get within some confidence interval of your estimate. And if you don't, the trade-off is exponential. That translates into an exponential cost in the number of
yeah,
replications.
but suppose you have a problem and there's no hope of finding a subsolution, and you've got very limited knowledge of the statistics. There's a robustness in the IPS that's not there with the ordinary one. The ordinary one is very, very precise when you can design it well.
Right.
But what this says is that there's a degree of imprecision that's allowed for the IPS scheme. It's true in terms of the measures that we usually use, where we want to get the best possible asymptotic rate of decay, but let's face it, many times you're not going to get the best possible asymptotic rate of decay. And so,
No, but precisely because you do not know, at the end you are going to have an estimate based on Monte Carlo. You are going to replicate the estimator that you have designed, and you don't really know if the confidence interval that you are obtaining actually tells you anything in practice. You need to select the number of particles so that the effort that you have spent by simulating is actually gives you a meaningful confidence interval, I would assume. In some sense, like taking n sufficiently large so that you can you don't need exponentially or many, not in practice many replications of that estimator is it seems useful, no? I mean, based on your theorem. You need to have C divided by n. Maybe it's extremely hard to get a subsolution, but you need to have reassurance that C divided by n, namely the loss, is not too big.
well,
I would assume.
I think that's an open, depending on the problem, that might be an open issue, I would say. Thank you.
Your real metric is the total computational cost. What's the rationale behind keeping the number of particles constant at each level?
Is what I'm saying. That's my question. That was.
Okay, I didn't understand your question.
Well, I mean, there
Yeah.
are potential problems. It's not just computational cost, it can also be just practicality in terms of writing down the algorithm. I mean, if you have an explosion in the number of particles, that you have to allocate certain space to finish the computation.
What I
I
meant
mean,
is you just you presumably have a decreasing number of particles at each level, so you just allow some of them to disappear rather than.
you don't necessarily. If you design it poorly, you could have exponential explosion in the number of particles. That's I think one of the main motivators for introducing the IPS system was to completely avoid that issue of the potential for an explosion in the number of particles.
I don't follow. You get to choose the number of particles that you simulate, right?
You do in the IPS. With ordinary splitting, you don't.
So the real question is, what is there might be some best way of choosing the particles as you march through the levels, which allows you to approach the true asymptotics in the best possible way, where your real metric is the computational cost. That's my question. It seems like fixing the number of particles is more motivated by the desire to do good analysis rather than.
Oh no,
solve the original.
I would argue completely the opposite. Does not make the analysis easy. It's the opposite.
Well, thanks very much.